Hi, thank you very much for coming. I'd like to, thank you. I'd like to especially thank Helen Caldicott, the Caldicott Foundation, and Physicians for Social Responsibility for sponsoring the meeting today. And for those of you on the feeds throughout the world, thank you for listening, likely at midnight in Japan. A downloadable PowerPoint presentation like I'm going to give is on the Fairewinds website for those of you in remote locations. And if you want to pull it down, go to Fairewinds. And there's also a Twitter conversation going on, as we discussed earlier, and also at Fairewinds on Twitter. Okay, let's buckle our seatbelts and get started. I wanted to talk today about when people knew there were problems at Fukushima Daiichi, both in the decades before the accident and then immediately after the accident. But before I do, there are hundreds of people at Fukushima Daiichi and at Fukushima Daini who I'd like to acknowledge as my personal heroes. This was an accident, a tragedy, and caused by a failure of technology. But what saved the day was human courage. So we have an example here of courage defeating failures in technology because of several hundred people who risked everything to save Japan and to save the world. And I am in awe of what they did. The sequence is the first two sections. I'd like to talk about what happened in 1965. What was known before this plant was ever started. And the second two presentations is what is known now after the accident. The Fukushima Daiichi accident was made in America. The reactor was designed by General Electric and built by a company called Ebasco. I used to go to the Ebasco offices right here in Manhattan when I was an engineer on Millstone Unit 1, which was almost identical to Fukushima Daiichi Unit 1. It was licensed by the Atomic Energy Commission, which at the time, in 1960s, was the ultimate authority on nuclear licensing in the world. At least we thought that to be the case. This is not just a Daiichi issue. There's 22 other plants in the United States that are similar. And the plants in the United States are in some ways much worse because there's a lot more waste fuel in their spent fuel pools than there were at Daiichi. The engineers at General Electric and at Ebasco made 6 critical mistakes in 1965 that were to doom Japan in 2011. The first 5 critical mistakes all revolve around the issue of not really understanding the power of a tsunami. They reduced the height of the cliff that the plant was built on. They built a short tsunami wall. The diesels were placed in the basement. The emergency pumps, called the service water pumps, were placed in a situation where they were underwater. And finally, the diesel tanks were placed in a place where they too were flooded. These were engineers based here in New York City that simply didn't understand the power of a tsunami. The last issue on the Mark I containment is a little broader, and I'll get onto that as well. This is a picture of the cliff at Fukushima Daiichi in 1960. It was 35 meters high, about 115 feet high. The engineers at GE and Ebasco cut it down to 10 meters, so it was a 30-foot cliff. This is a picture after Daiichi was built. These areas here and here are at 35 meters. The area along the seacoast is at 10 meters, and this is an access road cut down in through earth to get the plant close to the water. Well, tsunami is a Japanese word coming from tsu meaning harbor and nami meaning waves. The entire ocean rises up. If you're on a boat, you don't notice a tsunami because the entire ocean rises up, except when it hits a harbor, and then it becomes terrifying. It travels at close to the speed of sound. Engineers knew of tsunamis, and I thought I'd just go back 100 years in Japanese history to look at Pacific Coast tsunamis that hit Japan. In 1896, there was a 40-meter tsunami. 1923, there was a 13-meter tsunami. 1933, there was a 28-meter tsunami. And this was the tsunami of record as far as killing people before the Daiichi tsunami. 1944, there was a 12-meter tsunami. 46, another 12-meter tsunami. In 54 and 55, 10 years before Fukushima Daiichi was designed, there were 3 tsunamis, and all of them were over 13 meters. The tsunami that hit Fukushima Daiichi in 2011 was just a middle-of-the-road tsunami compared to the 100-year history before it. But in face of that history, the tsunami wall was built by American engineers at 4 meters and later raised to 5.7 meters. In addition, the diesels were placed in the basement. Now, diesels can be placed in the basement, but you should be able to put them in some sort of a waterproof container, which did not occur. It's important to know that General Electric built these first dozen or so Mark I reactors on what's called a turnkey contract. They took $60 million and built these plants, and they lost their shirt. I know because I worked on one of these turnkey reactors, Millstone 1, around the same time. So there was a lot of economic pressures on General Electric to keep the cost down because they were losing money dramatically on the dozen reactors they had built on this turnkey process. In addition, the service water pumps had to be at the water, but they were designed so that in any tsunami they would have been flooded. So it doesn't matter that the diesels were in the basement. If the diesels had been on top of the Empire State Building, we'd have the same problem because the cooling pumps that cool the diesels would have been flooded. In addition, the fuel tanks that provide fuel for the diesels were also in the floodplain. So again, it's not about the diesels being flooded. It's about engineers here in New York City, General Electric engineers and Abasco engineers who didn't appreciate the magnitude of a tsunami. This is an example of the, this is the height of the seawall. And of course, the pumps were totally inundated. The site was at 10 meters, but there was 4 meters more water on top of that. That's a 12-foot flood on top of Mother Earth. It was almost at the bottom of the control room. That's how much water there was on the site after the tsunami. Now, there's some political issues going on as well. General Electric, whose motto, by the way, in 1960 was "Progress is our most important product," said in 1961, they said, "We're going to ram this nuclear thing through." Their chairman is quoted as saying that. And ram it through they did. They met with the Advisory Committee on Reactor Safeguards, which in theory is an independent body designed to protect Americans in this case, but those design decisions were driven into the Japanese design as well. And Dr. David Ockert, who was on the advisory committee, basically said that General Electric threatened them of going out of business unless the advisory committee continued with this Mark I design. Scientists in the United States, 1965, recognized that this Mark I design had flaws, and as Dr. Ockert said, I think it was kind of a threat. Now, Glenn Seaborg was the chairman of the advisory committee at that time, and he actually has an atom named after him. He's got an element, a seaborgium, named after him. This is a heavy hitter in the nuclear industry. And he said, I don't think we had the power to stop them. Now think about that. This is the United States government didn't have the power to stop General Electric's faulty design in 1966. Just about the time the Daiichi units were starting up in '72, there's a famous letter exchange with a senior scientist at General Electric named Joseph Hendry. And Mr. Hendry said that he had serious doubts about the Daiichi design, the Mark I containment. But as I've highlighted at the end, he said that he felt they should be eliminated. But in eliminating this Mark I design, quote, it could well mean the end of nuclear power, creating more turmoil than I could stand. So the turmoil he chose to avoid in 1972 became the turmoil that Fukushima Daiichi experienced 40 years later. So when this plant started up, a made-in-America design, this is Fukushima Daiichi 1, units 2, 3, and 4 aren't built yet. Fukushima Daiichi 1 was built by General Electric in Tabasco on a turnkey project. There was no Japanese engineering on Fukushima Daiichi 1. All of the critical problems that Daiichi was to face 40 years later were in place. Essentially, the fuse was lit on Fukushima Daiichi in 1970, and it exploded in 2011. If we fast forward 40 years, this is the completed site right before the accident. And this is the tsunami hitting the plant. The earth sunk a meter, 3 feet, after the earthquake. The tsunami was 15 meters high. But remember, it's moving at the speed of sound, so the wave, when it hit the plant, actually crested at 46 meters high, over top of all these buildings. So how bad was it? The secret is in the assumptions. This is my favorite comic strip in the whole world, and for those of you who can't see it, I'll read it. Dilbert's being asked by the pointy-headed boss, and he says, I can do this feasibility analysis in 2 minutes. And then he says, it's the worst idea in the world. Numbers don't lie. Then the pointy-headed boss says, but our CEO loves the idea. And Dilbert says, luckily, assumptions do lie. So the message is here, when we're evaluating the dose consequences of Fukushima Daiichi, the secret is in the assumptions, which is where I'll spend the rest of this presentation. Assumption 1 is that containments maintain their integrity. After all, they are called containments for a reason. They're meant to contain. No containment in the world is designed to handle a detonation shock wave. That's a shock wave that travels faster than the speed of sound. There's 440 nuclear reactors, and none of them can handle a detonation shock wave, a shock wave that travels faster than the speed of sound, because engineers believed that it couldn't happen. Well, right after it did happen, it's interesting that the NRC's own Chuck Casto, now he's a senior guy. He's in charge of the NRC's Region 3 out of their Chicago office. A very senior guy at the NRC said this, of course, that Mark I containment is the worst containment we have. And if you have something called a loss of offsite power or station backout, you are going to lose the containment. There's no doubt about it. So remember that Mr. Hendry at the NRC in 1972 said this was the worst containment in the world. And here's the Nuclear Regulatory Commission saying the same thing immediately after the accident. We've known for 40 years that this Mark I design, like at Daiichi, was an accident waiting to happen. Well, what does a meltdown look like? When I was in the industry, someone gave me some nuclear fuel rod. It didn't have nuclear fuel in it. And right after the accident, I heated it up to 2,000 degrees. This is what nuclear fuel looks like at 2,000 degrees. This is what was going on inside the reactors at Fukushima Daiichi when they didn't get their cooling order. It's pretty hot. Okay, this is a time lapse. I'll shoot through it really quickly. Fukushima Daiichi units 1 has already exploded. It's on the far left. Then Daiichi 2, 3, and 4. Keep your eye on Daiichi 3 in the middle. Right there is the beginning of something that the NRC believes can't happen. That's a detonation shock wave. right there. There's the building intact. There's the building erupting with a detonation shockwave. Now, this can't happen, so don't worry about it. These are time-lapse of the detonation shockwave, and of course, you've all seen the devastation that a detonation shockwave can occur. Containments were meant to contain, and this is not supposed to happen. Assumption number 2 is containment leakage. Now, Dave Lochbaum was on top of this back before the accident, and certainly during the accident, as was Fairewinds. What happened inside the Daiichi reactor was that the pressures got so high that the bolts that hold the containment together began to stretch. And hot radioactive gases and hot radioactive steam began to leak out, and hydrogen. Now, in addition to the hydrogen that was created in the fuel, there was already a meltdown in process, and that fuel was now lying up against concrete. The concrete was liberating hydrogen as well. So we had 2 sources of hydrogen after the Daiichi accident. The fuel, as it created something called the Zirk water reaction, zirconium water reaction. But we also had the meltdown was causing more hydrogen because the hot fuel was in contact with concrete, and that was liberating hydrogen as well. Now, the NRC assumes that containments leak at 1% a day. So in a building this, in a room this size, what we're saying is that the gases that are released would be about 1%, meaning over 100 days, the gases in this room would leave and fresh gases would come in behind it. But what the NRC said in a phone call on March 23rd is that the reactors at Daiichi were leaking at 300% per day. That means that the gases inside Daiichi were leaving the containment every 8 hours. Whatever radiation was getting out of that nuclear fuel was being liberated to the environment within 8 hours because the containment leak rate was 300% per day, not 1% like the NRC assumes. Assumption number 3 is noble gases. Now, if you remember your high school chemistry, raise your hands if you do. I don't see many hands. Oh, I do. The far right of the periodic table is our noble gases, things like neon and krypton. They're called noble because they don't react with anything. Nuclear fuel is loaded with noble gases, and as long as the fuel retains its integrity, the gases are trapped inside. Well, the fuel didn't retain its integrity, and all the noble gases were released. The data indicates that over Chiba, the xenon, which is a noble gas concentration, was 400,000 times normal immediately after the accident. And also that the concentration of xenon in Chiba was 1,300 becquerels per cubic meter for 8 days. Now, a cubic meter is about 3 feet by 3 feet by 3 feet. And think about it, inside every cubic meter of air over Chiba, there were 1,300 disintegrations emitting radioactivity every second for 8 days. What were those people breathing? Gases with noble gases, which can't be monitored now. They're gone. So I think one of the issues here is that the Japanese government has no idea how much exposure the people in Chiba got from this cloud of noble gases that were released. This is important data that just came out. Mainichi covered this story, but it's actually Fukushima Prefecture data, and it's only a couple of days old. There were 4 radiation detectors that continued to work after the Daiichi accident. Almost all of them didn't have power, but a couple were battery powered, and they just recently discovered the data. Normal background on these radiation detectors was about 0.04 microsieverts. At 5 o'clock in the morning, right after the accident, the radiation in the detectors was 10 times background. 6 o'clock, 60 times background. 9 o'clock, 150 times background. 10 o'clock, 700 times background. What that means is that somebody in the vicinity of these radiation detectors was getting a yearly dose in 12 hours. Then the vents were open. So this is a clear indication that the containments were leaking well before the vents were open. So at 3 o'clock, these same detectors were measuring 30,000 times background. That means a yearly dose in 10 minutes for the people in Chiba. Now, it's also important to realize this may not be the worst. This happens to be where the detector was, but it doesn't mean that the plume chose to go to the detector and get that reading. This is a complicated slide, but it shows exactly what I did talk about here geographically. The one detector was here. Well, here's the plant. One detector was here. Here's its spike. Another detector was here. Here's its spike. Another detector was here. Here's its spike. So it geographically ties this data around. So it's clear that this plume was meandering all over the western side of the plant and the northern side of the plant, even before the vents were open. Also, one of the detectors continued to operate, and here's the spikes in the detector. There's no correlation between these spikes and when the venting occurred and when the explosions occurred. There's no correlation, which means that other phenomena had to be happening as well that scientists have not yet evaluated. Assumption number 4. The decontamination factor for cesium, and I'm sorry, this is a little bit geeky, but the Nuclear Regulatory Commission assumes that after a nuclear accident, the water inside the torus, which is the donut at the bottom of the containment, takes out 99% of the cesium. That's called a decontamination factor of 100. That's actually written into law, that they believe that to occur. But they also say that if the water hits boiling, there's no decontamination factor. The water is incapable of capturing any cesium. Well, the data from Fukushima shows that the water in that torus at the bottom of the containment did boil. Why did they boil? Because those cooling pumps I was telling you about that cool the diesel were also designed to cool the torus. So we had boiling water in the torus, and that meant that no cesium was retained. Now, the Japanese, as they're trying to reconstruct this accident, are claiming cesium was captured inside that torus, but the law and the data show that it couldn't be. There was no cesium deposition, no cesium retention inside the suppression pool. Now, how do I know that? This is an important slide. It's kind of blurry. It's an infrared image of Unit 3. The large blotch in the center of the screen is the spent fuel pool on Unit 3. That's here. And the temperature of the gases coming off the spent fuel pool are 62 degrees centigrade, which means that the fuel is boiling and it's mixing with cold air, and there's a bath of hot radioactive air over the fuel pool at 62 degrees. That's pretty bad. But what's worse is the flare that the drawing shows. Now, TEPCO's known about this for 2 years and has not talked about it. That flare right here is exactly where the containment should be. And that flare is at 128 degrees Celsius, which means it's not steam. Steam can't exist over 100 degrees. Engineers call this something in the steam tables. But at atmospheric pressure like we are today, when you boil steam, you're only going to get to 100 degrees centigrade. That flare is at 128 degrees, which means that it's not steam. It means it's hot radioactive gases being released directly from the containment. It also means that inside the containment, it was not below the boiling point of water. It was above the boiling point of water. There was no liquid water inside that containment. This is on March 20th, 9 days after the accident. The containment is venting hot radioactive gases directly to the environment. This is proof positive in my view. And TEPCO, obviously, they're good engineers, and they would have seen that 128 degrees centigrade, about 250 degree hot radioactive flare being released in this infrared picture. So they've known for a long time that huge amounts of cesium were being released directly to the air because they weren't being trapped in the water in the suppression pool. The last assumption is hot particles. This is me and Reiko, my co-author of the book we wrote in Japanese, taking a sample when I was in Japan in February of last year. The soil, I took 5 samples in 5 days. I just went to a piece of pavement or a piece of, one case it was a children's park right next to a school. The kids were playing right next to me, throwing stones like kids do. I took a bag of samples. And I brought the 5 samples back, declared them through customs, and they were analyzed by Marco Kaltofen at Worcester Polytech. And each of the samples exceeded 7,000 becquerels per kilogram. What that means is in a 2-pound box of sample, we were getting 7,000 disintegrations per second of cesium in Tokyo, more than 100 miles away from the accident. Think about that. That's like, you know, New York City, Tokyo and New York City, roughly comparable as far as the importance to their nation. And 7,000 becquerels per kilogram qualifies as radioactive waste in the United States. So the people in Tokyo are walking around with spots that have radioactive waste. And I didn't go hunting for this stuff. It was right on the side of the sidewalk. This is an autoradiograph of a car filter in the take-in. What that means is we had people, Fairewinds had people send us air filters. And one box arrived, totally unexpected. And as I approached it with my Geiger counter, the Geiger counter started to go off at 5 feet away. It was a car air filter. We took the car air filters and laid them out on an X-ray plate. Marco Kaltofen did at Worcester Poly. And these are the burn marks in the X-ray plate after the X-ray plate was set in a safe for several days. Fukushima Daiichi's on the right, Tokyo's in the middle. Those show hot radioactive particles trapped in the air filter. Well, people were in those cars. Kids were in those cars. If it's in their lungs, if it's in their air filter, it's in their lungs. I think it's safe to assume that the people in Fukushima City and the people in Tokyo had enormous exposure of hot particles directly into their lungs. We also asked for kids' shoes. This is the concentration of cesium on children's shoes. Kids tie their shoes. Kids eat with their hands. That's in their stomach, it's in their gut, it's in their intestines. I thought I'd compare what the available inventory of radiation was for cesium compared to Fukushima Daiichi. Now these things are called petabecquerels or petabecquerels, and it's a whole bunch of zeros on the end of a number. The total available cesium at Chernobyl was 2.9 with 17 zeros behind it of cesium. There was almost 3 times more cesium available to be released at Daiichi 1, 2, and 3. We know for a fact that 300%, 3 times more noble gases were released from Daiichi. There can be no argument about that. Now people are wondering how much cesium was released. Chernobyl shows that about 1/3 of the cesium was released from Chernobyl. And Japanese experts are saying that, oh no, it can only be about 1% of the cesium was released, or maybe 2% of the cesium was released from Fukushima. I don't believe that's true. And I don't believe that's true because of the drawing I showed you before, where the temperature inside that reactor was on the order of, inside the containment, was so hot that there was no liquid water to retain the cesium. The Japanese experts believe that the cesium was retained in the water. But that infrared photo that I showed you earlier clearly shows that couldn't have happened. So I conclude that the noble gases were 3 times the releases of Chernobyl, and the containment leak rate was 300% per day. That's an NRC number. Tokyo has 35 million people in metropolitan Tokyo. And Prime Minister Khan said, our existence as a sovereign nation was at stake. Now, I already know, I've taken the 5 samples that show that portions of Tokyo, all over Tokyo, were as radioactive as what we would have to send to a radioactive dump here in the United States. So I think the point is, at what point do the risks of a technology become unacceptable? Well, my conclusion is that sooner or later, in any foolproof system, the fools are going to exceed the proofs. Good. Thank you.